Okay, the first thing that we're going to do is I'm going to fill in the last two tabs of that foldable. So I will have scissors. I forgot to pass them around the other day. But we've already talked about a horizontal shift, a vertical shift, reflect over x-axis, reflect over y-axis. Those were where we are moving the graph around, and then it's either reflecting over the x-axis or reflecting over the y-axis. So now we're going to fill in the two parts that have to do with the vertical stretch and compression and horizontal stretch and compression. So on your blue foldable, that's where I'm going to put this information. So I'm going to kind of scroll like I did last time to a new page, just so I have it. And if you, for some reason, don't have your blue foldable with you and you need to write this down at the very bottom, there should be room on the back of these notes if you don't have it. But if you do, I'm filling in these 4 boxes at the very bottom. So the first section we're going to talk about is the vertical stretch or compression. So the way that we see those is it should have a multiplier in front of your function. So when I say in front of, in the same place where we saw the reflection over the x-axis, that is where you would see a vertical stretch or a vertical compression. So we have 2, and I'm just going to abbreviate. I know yours is fully spelled out. Vertical stretch, vertical compression. So the first thing you have to do is decide which one am I looking at. So if the A is bigger than 1, so 2, 3, 4, 5, 6, 7, anything bigger than 1. Technically, you can even do like 1.5. That's bigger than 1. If it's bigger than 1, it's a vertical stretch. And you apply this by multiply y values by A. So whatever number you get. So if I have a 2 at the very front of my equation, all I'm doing is multiplying my y values by 2. So the other side of the coin is a vertical compression. So that is when A is between 0 and 1. And a lot of times people want to look at this and say when it's a fraction. Mostly true, but if you had something like 3/2, technically that's bigger than 1. And so that falls into vertical stretch category. But like 1/2, 1/3, 1/5, 2/6, 4/5, whatever, those are all vertical compressions. But the nice thing about these is we apply them in the same way. Multiply y values by A. And I sometimes like to include an example in this little foldable just so you have it. So somewhere near vertical stretch, you can say like 2, and then we have x squared would be a vertical stretch. And then for vertical compression, 1/2 x squared. And the parentheses don't necessarily have to be there in that case, but I want you to see that this multiplier is outside. Now, when it's inside, it would be in with the parentheses that are currently there. So this is our vertical stretch, our vertical compression. It is only going to affect the y values. If you need to make yourself a note, you can even say x values don't change. And being the teacher who writes the test, we will never ask you to do both at the same time. So like we won't have you do a vertical stretch compression and a horizontal stretch compression. It's always just going to be one only. So this is vertical. Now horizontal works almost exactly the same way. So I have the horizontal stretch or compression. Let me go in. Now this is the trickier one because the way we write it kind of works in the opposite sense you would think it does. So horizontal stretch compression. So basically, if I have a function and there is a multiplier inside. So notice the b is inside the parentheses of the function this time. So that would be like a reflection over y-axis. It's inside the function. And just in the same sense of things, we can say y values don't change. And you'll notice that when I write these out, I I will immediately first go in and write the values that don't change, just so I make a note to myself that these I'm not touching at all. So then we're going to go in and we're going to do, let's see who's here. Somebody tried to get in. Or maybe not. Just kidding. I thought I heard somebody. Horizontal stretch, horizontal compression. So it's kind of flipped in the way you would think. Horizontal stretch, horizontal compression. So when B is between 0 and 1, so they kind of flip, they swap what they normally do. When we had a vertical stretch or compression, it was when A was bigger than 1. When we have a horizontal stretch, it's between 0 and 1. This is going to be where we multiply X values by, now here's where it's tricky. We're technically multiplying by 1 over B. So whatever number we get that's in front, we're technically multiplying by the reciprocal is what we call it. Bless you. Same thing over here. B is going to be greater than 1. Multiply X values by 1 over B. And again, I know the fear is we don't have our calculator. What are we supposed to do? How am I supposed to multiply? We're not going to give you huge numbers. You're going to do things like, what's 4 times 2? What's 3 times 6? Or not even that big, 3 times 3. We're not giving you things that are so out of the realm of like a 12 by 12 multiplication table. They are things that you should know. We're not going to expect you to be multiplying like huge numbers together and then graphing them. It is the basic math facts that you've probably learned your whole entire life. Now, one little note here, because I don't want it to get too crazy when we actually look at it in the graphs. If I had the same function and there was a horizontal stretch, it would look 1/2 x squared. It would look like this. So again, following the rules that we have, the horizontal stretch happens when the multiplier is a fraction on the inside. So notice I have a 1/2 on the inside of this quadratic function. However, when I go to apply it and I do 1 over 1/2, very long ago, maybe I can ask an Algebra 1 teacher, you probably did it in Algebra 1, but whenever you divide a fraction by a fraction, you do something called keep, change, flip. So actually what we're multiplying by is the denominator too. And I'm telling you this because I don't want us to have to do this every single time, but when we do a horizontal stretch, all we're doing is multiplying by the denominator. And so when we write this out, we say horizontal stretch 2. And then for the horizontal compression, it's the same thing. If I go in and I see 2x squared, and it's a whole number on the inside, that is a horizontal compression. But when I go to multiply by 1 over b, I'm multiplying by 1/2. So it's kind of like you're thinking in the opposite way. For the most part, you're probably not going to have to graph these on the test. Usually it's mostly identification. We will graph them today. We will practice graphing, but it's more on the side of pre-cal, and we're kind of getting you ready for geometry, which is what you'll do next. So we will talk about these, we will graph them, but just know that when you're looking at the horizontal stretch and compression, thinking oppositely of what you would normally do. So let's go in, let's try this out. So we have our transformations. A lot of these you should know. I'm going to give you a little reminder of things we've already discussed. We've discussed that this is a reflection over the x-axis. This is a reflection over the y-axis. This plus h is how you move left, right. This minus k is how you move up, down. So those are the 4 transformations we learned in 1.2. The 2 new things that we're discussing today is if you have an A at the front, it's a vertical stretch or compression. And you will be asked to identify these, so knowing where everything is helpful. And this is our horizontal stretch and compression. So 6 transformations total. We don't have graphs realistically that are going to have all 6 things at the exact same time. The most transformations you may see is like having a reflection and a stretch with the shifts, but you're not going to have like double reflection, double stretch, moving it left, moving it up. Like, we're not going to do that to you. So make sure you know where they are because you will be asked to identify them. So going through our reminders, when we graph, the first thing we do is we identify our function because we need to know our key points. And then we move the origin left, right, up, down. Same thing as we did from last time. If you are reflecting over the x-axis, that's going to change the sign of your y values. X values change if you are reflecting over y. Vertical stretch or compression will multiply the y values, and horizontal stretch or compression will multiply the x values. So I like to have those reminders in there just so you have a reference point back to why are we multiplying the x's and not the y's. They are all tied to what type of transformation you're actually looking at. So let's go in. Now, I got a lot of questions last time. How do I know what parent function I'm looking at? Process of elimination. The first thing I would ask myself is, does it have absolute value bars? No. And then I would say, okay, well, does it have a radical, a little root? No. So that eliminates square root, that eliminates cube root. Those are gone. So that leaves me with quadratic and cubic. Quadratic will always have a little tiny 2. Cubic will always have a little tiny 3. So in this case, there's a little tiny 3. So that means this parent function is a cubic function. So I like to kind of write in what the parent function would look like with no transformations so that I can come in and identify how does it differ. We always start with shifts. So usually when I write these down, I will write my shifts first. So what I'm noticing is I have a +1 on the inside and a -6 on the outside. That +1 is always going to do the opposite of what it looks like. So instead of moving to the right, this graph is actually moving to the left. So this is going to go left 1. Always do the opposite on the inside. Now the plus or the -6 is on the outside, so that means we are going to move exactly what it looks like, down 6. Generally, my recommendation, whenever you're graphing this, start by shifting the origin. The origin normally sits at 0, 0. It's now going to move left 1, down 6. So I like to come in and draw my new x-axis and y-axis. So left 1, down 6. And this place where they intersect is going to be like my new 0, 0. Now we go in, and that's nothing new. That's exactly what we did in 1.2. The new part is I now have a 1/2 at the very front. Now notice that this 1/2 is not sitting in a set of parentheses. If it is not in parentheses, it is outside the function. If it's outside the function, it's vertical. Now, we know this has to be a vertical stretch or compression. The way you decide for vertical is if it's bigger than 1, it's a stretch. If it's between 0 and 1, it's a compression. So this is a fraction, a 1/2. That means it's between 0 and 1. So this is a vertical compression, and we always list the value, 1/2. And we're always listing what we actually end up multiplying by. So I'm going to multiply all of the y values by 1/2. And if you need to make yourself a note, multiply y values by 1/2. So another thing that this will hinge on, what we asked about in your quiz today, was you knowing your parent function points. So when I have a cubic, there are 5 points that we should know in terms of being able to graph this. So I'm going to list all 5. You, on your paper, if you're comfortable with your points at this point, you don't have to actually list them out. I do think it's helpful. -2, -8, -1, -1, 0, 0, 1, 1, 2, 8. So these are all of the key points that we say you are responsible for when it comes to the cubic function. Now, I'm not reflecting anything, so I don't have to worry about changing any signs, but I am going to go in and multiply all the y values by 1/2. So I'm going to kind of draw a new set, and this is what I'm actually going to graph. Since the x values are not changing, I'm going to go in and just write them out as they should be. So -2, -1, 0, 1, and 2. And then every single y value that I have from my key points, I'm going to multiply it by 1/2. So if I go in and multiply by 1/2, it's like I'm dividing. So if I take -8 and I divide it by 2, what do I get? What's -8 divided by 2? 4. So is it positive or negative? Negative. So -4. And then if I take -1 and I divide it by 2, I get -1/2. Yep. So -1/2. The nice thing about a lot of these functions, 0 divided by 1/2 is still 0. The nice thing about a lot of these functions is they have some type of values where they're going to repeat themselves. So when I go to the other side of my cubic, because of the fact that it has rotational symmetry, I do have the same values, they just change signs. So I have 1/2 and I have -4, or +4, sorry. And so what we're going to do from our origin, our new origin, I'm going to plot these points. So 0, 0 is no longer at the intersection of the x and the y axis. 0, 0 is going to be at the intersection of where I moved left 1, down 6. And the way I count the other points, I take my little pencil and I go right 1 and up 1/2. And that's where I'm going to draw my next point. And then I go right 2, up 4. And that's where I'm going to draw my next point. So I'm literally doing the exact same steps we did last time. It's just now the values are changing versus only changing sign. So 1, 1/2. And you can kind of just eyeball it as best as you can, because I know 1/2 is not a tick mark on your paper. And then the nice thing is it's going to have rotational symmetry. So 1, 2, 3, 4. It should just continue the same way on the other side, just downward. Connect your points. And you should have a cubic function that looks like it was kind of squished together a little bit because we compressed it instead of stretched it and made it skinnier. Now, the really, really nice thing about cubics and cube roots is there are never any restrictions. It doesn't matter what you do to this graph. You can reflect it, stretch it, compress it, do all of the transformations you want to it. The domain and the range are always going to be -infinity to +infinity. Every single time. So even if you get to the test and you're like, man, I cannot graph this cubic function, you should still get the domain and range right. Because even if you graph it incorrectly, it's always all real numbers every single time. So cubics and cube roots have no restrictions whatsoever. Do I have any questions on number 1? Okay. So let's go in and let's kind of look at what we have next. Again, process of elimination. I don't have absolute value bars. I don't have a radical. I see a little tiny 2, so that tells me my parent function has to be a quadratic. And so that means it should look like y equals x squared without any transformations whatsoever. Always start off with your shifts because those are the easy ones. Inside, I have a -3. outside, I have a plus 3. What does that minus 3 tell me? Right 3. And so that means the y-axis is shifting to the right 3. What does the plus 3 tell me? Up 3. So I'm going to do up 3. I'm going to do right 3. And where these two lines intersect is going to be my new origin point. Now, this is where I'm going to treat 0, 0. So the next part is going in and identifying the stretch or compression. The first thing I'm noticing is it's inside the parentheses. If it's inside a set of parentheses, it is going to be horizontal. And so here is where you're deciding, is it a horizontal stretch or is it a horizontal compression? So with the stretch, why do you say it's a stretch, Zite? Because it's less than 1. So think about this in terms of it's flipped. So normally when we saw a 1/2 in number 1, it was outside, we said it was a compression, but when we look at it horizontally, it's actually going to be a stretch. So we're going to say horizontal stretch. Now this is the tricky part, because the way we actually apply a horizontal stretch is we multiply the x values by 1 over b. And I told you, in order to simplify this for yourself, don't think too hard about it. Whenever you see this fraction, you are just multiplying by the denominator. So I am going to multiply the x values by 3. Now, when I state this as a horizontal stretch or a compression or vertical stretch or compression, it's always based on what is the multiplier. And so since our multiplier is 3, I'm not going to say horizontal stretch 1/3. I'm going to say horizontal stretch 3. So this is one where it's going to kind of do the opposite of what you would normally think. And that's only because we are technically multiplying those y values by 3 and not 1/3. So quadratic points should hopefully be some that you know pretty well because you did them in Algebra 1, 4, 5. -2, -1, 0, 1, 2. And these are all coming from your pink foldable. If you're like, where the heck is she getting these points from? They're in the pink foldable from the parent function video. These are the 5 key points we'll always ask you to graph for a quadratic. So -2, 4, -1, 1, 0, 1, 4. Because a quadratic is a little U shape and they're all positive values. Because anytime you square something, a negative times a negative is a positive. So once we have this, I'm going to go in, and this is telling me that we're changing the x values. So before I do anything else, I'm going to change, or write, my y values so that they don't change. So that's a 4, 1, 0, 1, 4. No change to those. The only thing that's changing is the x. And I'm going in and I'm multiplying all of my x values by 3. So I'm going to take -2 times 3, which is -6, -1 times 3, which is -3, 0, 3, 6. So all you're doing is multiplying. And again, notice, none of the multiplication is impossible. The biggest one you've had to do so far is 6 or 2 times 3. So you don't need a calculator for that. You can do those multiplications on your own. So once we graph this, I always put 0, 0 down first. And then I'm going to count 3 to the right and 1 up. And then I'm going to count 6 to the right, 4 up. 1, 2, 3, 4. And the nice thing about quadratics, their kind of feature, is it has reflectional symmetry. So if you can graph one side, you should be able to graph the other just by having it mirror what's on the other side. So I know I have to go left 3, up 1, left 6, up 4. And you should get a parabola that kind of looks like it was stretched out on the x-axis. And one thing that you'll find if you really think about it is when you identify these horizontal stretches and vertical compressions, there's ways to describe this in both senses. Because technically, this was vertically compressed, but when I vertically compress something, I'm horizontally stretching it. So there are multiple ways to describe this. We generally only have you do one. So when we go in, domain for quadratics, does not matter what you do. Negative infinity to positive infinity every single time. Does not matter what you do to that quadratic. Reflect, stretch, compress, any type. The range, however, because we moved up 3, it's going to start not at 0 like the parent function would. It's going to start at positive 3 and it's going to have a bracket because there is a point there all the way to positive infinity. Okay, we've done vertical compression. We've done horizontal stretch. So it looks like vertical stretch is up next for us. So on to the back. Vertical stretch. So I see a radical. And then the next thing when I look at the radical is, does it have a little tiny 3? I'm going to give you a little piece of advice. Notice that this looks like 3 and a big radical. If this were a cube root, that 3 would be a very tiny 3. So we will get the question of like, is this supposed to be a cube root? It will look like a cube root if it's supposed to be a cube root. Just because there's a 3 in front does not make it a cube root. It would be a little tiny one if we wanted it to be that. So in this case, we actually have a square root. So y equals square root of x. There's highlights for all of them, but for square root, the nice part is you only have 4 points because there's only 4 points that we can really guarantee are going to fit on a 10 by 10 grid. And that's because we have to take the square root of these values. We're not going to make you do things like take the square root of 5. It's not a nice number. We're not going to have you do that. But the square root of 4 is a nice number, so that's one of our key points. Transformations, we have a plus 7 on the inside, which means we're going left 7. And we have a plus 4 on the outside. I did get the question last class of, can I combine the plus 7 and the plus 4? What I want you to notice is when that radical ends, it's kind of like a parentheses. So that radical is the cutoff for what's inside the function. So since one number is inside and one number is outside, you cannot put them together. We will never try to trick you and be like, oh, you were supposed to add them together. I can't believe you didn't see that. No. If it's underneath the radical, it's inside. If it's outside the radical, it's outside. So this is going to be up 4. So I'm going to go in, left 7, up 4, and draw my y-axis and my x-axis. And again, this new intersection is going to become my new origin. Now, this particular function has 2 other types of transformations. The big thing that I want you to know, you cannot say vertical stretch of -3. The vertical stretch itself is the 3. The negative is a different transformation. When we had a negative at the very front, what did we say that was? Reflection. So if it's on the outside, it's going to be a reflection over the x-axis. If it's on the inside, it's a reflection over the y-axis. So this is reflection over the x-axis. Now, whenever we did a reflection over the x-axis, that changed the signs of the y values. So anything that was positive is negative, is positive. Now we have the 3. The 3 is a vertical stretch of 3. Stretch of 3. Now, what I'm going to tell you, whenever I have both of these transformations at the same time, So I have a reflection and I have a stretch, and they're both going to affect the y values. You can apply both of them together. So what I'm actually going to do is from both things, from the vertical stretch and the reflection, I'm going to multiply my y values by -3, because negative is going to change the sign of every point, and 3 is going to stretch every point. Yes, Ite? You can do it mathematically, but when you name it, you have to name it separately. So you have to list the reflection, which is the negative, and you have to list the vertical stretch. We can't say vertical stretch of -3, but we will apply it together. So I'm going to do 0, because 0 is not changing, 1, 4, 9. And then all of those values are going to get multiplied